All right, everyone. Thanks for coming. Welcome to the wave class. Now let's try to be quiet, pay attention, so that we can be as efficient as possible. So I think this is going to be an interesting subject. This is going to be an introduction to a lot of different interesting math and science. So if you're interested in doing anything math and science, you'll find it interesting. But even if you're not, there's all kinds of interesting applications of waves, no matter what you're doing in life. So, for those who don't know, my name is Caleb, and I've been studying waves for basically 13 years, off and on, different topics. I've done sound analysis kind of stuff, radio hacking, art, all with wave mathematics. And so there's this great quote by Nikola Tesla: "If you want to find the secrets of the universe, think in terms of energy, frequency, and vibration." Hey, can I have that yo-yo?
I'll play if it's just to
No.
keep it out of the way.
Okay, so if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. In other words, think in terms of waves. So Nikola Tesla is a famous scientist who invented all kinds of stuff. AC current, a lot of the Tesla coil. But that's a big statement for a scientist like that to make.
If you know who invented Tesla,
The company Tesla was named after him.
it's
Yeah.
run by Elon Musk.
Mm-hmm. All right, so there's all kinds of waves. All kinds of waves. Waves are one of the most common patterns of any kind in nature. So if you look at the Wikipedia page for patterns in nature, you'll see some of the patterns are symmetries, which means like when things look the same, like your face is usually symmetric, right? That's a kind of pattern in nature. Spirals, but waves are even the one that's shown at the top. Here, let me see this. Waves are the one that's even shown here at the very top of the Patterns in Nature page. But before we go further, I'd like to see, can any of y'all think of what kind of waves come to mind when you think about waves? Ocean waves. Yep, that's a good one.
Sound waves.
Music, good.
Light waves.
Sound waves, light waves.
Microwaves.
Microwaves. Art. Yep.
Radio waves.
Radio waves.
Radiation waves.
Yeah, lots of good ones. So a few types of waves. Obviously, ocean waves come to mind for a lot of people first.
There's a baby in there.
Rave, stop.
In the middle of the wave. Is that just me?
Don't do it right now. It kind of looks like that, but so obviously obvious ones like ocean waves and stuff. But here's an interesting one to think about. Literally all communication of any kind happens through waves. For example, right now, you're hearing my voice because my vocal cords are creating pressure waves in the air, which are hitting your eardrums. And that's why you can hear me. That's how we can communicate. Also, light waves, right, are a kind of wave. So if I was doing some kind of signal and you're able to see it, you're only able to see it because of light waves. Radio waves, yep. We can communicate with our cell phones and stuff like that. But again, it's waves, right? So just listing a couple, all communication, sound waves, light waves, radio waves. We already mentioned all these. Water waves, land waves. We live in the mountains, right? Mountains are waves made of land. Heartbeats, right? At your very core is your heartbeat, and that's the kind of wave. Breathing is a form of waves, right? You got it. You breathe in, and you breathe out. There's kind of this in and out, up and down kind of pattern. It's waves. Brain waves. Your mind even runs on waves. Music. So the more you study music, Huh?
Music is for sound.
It is, but it's not. But it's interesting because even the kind, if you pay attention to how music is formed, like I got actually an example of like if you listen to this song, for example. Repeating pattern, right? Music, it's all these waves basically. So, music, all matter. This is another one you may not think about. Modern physics has basically been indicating that all matter is actually made of waves as well. So even things that we call particles, things like photons or electrons or neutrons, are actually made of waves. So radio waves are one, we mentioned it, and I want to have a little demo of an interesting kind of hacking demo a little bit here in just a minute, dealing with radio waves. And we talked about radio waves, but there's different kinds of radio waves. There's FM radio, when you turn on the radio and you have the FM or AM dial, right?
What's the difference in FM and AM?
Good question. FM stands for frequency modulation, and AM stands for amplitude modulation. Modulation basically just means changing something, okay? So amplitude modulation is like changing the volume, like this. Frequency modulation is changing the frequency. So the volume doesn't change, but it goes like this. Okay, so that's kind of the difference. They're also at different frequencies. But Wi-Fi. Wi-Fi, all of our computers use Wi-Fi. That's also radio waves. So is Bluetooth.
Is there a way to have a computer without Wi-Fi?
Yeah, you just won't have internet.
It is so hard to do things, look up things without internet.
Right. Yep. Bluetooth, you know, right? If you got Bluetooth speakers or headphones, that's also radio waves. GPS, even the satellites that are sending your location on your map is also done through. No, they use the form of triangulation, but ultimately there's satellites that are sending signals to your GPS receiver like on your phone, and it's also radio waves. Wireless security systems, keyless entry on your car, right? So like you got keys and you can lock and unlock your door, right? That's actually radio waves as well. Many other things. Streaming waves, yes. Now, so it's kind of odd to think about how many kinds of waves are actually radio waves. But this is a really good chart. Rafe recommended I include this. So just to give an example, there's lower frequency waves. We'll talk about what frequency is in just a minute. Lower frequency waves up to higher frequency waves. Generally, lower frequency waves have what you might call less energy in them, and higher frequency waves have more energy. They're also, so because these are all in the medium of electromagnetic radiation, the frequency means more energy. But also, lower frequency means bigger waves. So if you ever see those giant antennas that radio stations have, for example, they have to be really big because those waves are physically that big. So radio waves are as big as buildings. Like 10 to the third power is like 1,000 feet high. No. So the physical waves that are AM radio, those waves are 1,000 feet tall. Okay. Microwaves are about the size of butterflies. So the waves for microwaves are very small. How about light? So interestingly, the radio waves are made of the same stuff as light. Light is just a higher frequency than radio waves. That's kind of interesting. Now, the light waves are very, very small. They're like the size of a needle tip. So they're microscopic. And then, you've heard of X-rays, right? Those, you can see through your body with those. All the way up to what you might consider the most dangerous form of waves, gamma rays. Anyone know where gamma rays come from or anything like that?
Nuclear explosions from stars and atoms.
Yeah.
The sun?
Yeah, they can come from the sun, explosions of stars, nuclear explosions, but they're so powerful that gamma rays can cause damage if they hit you. So, you hear about death rays in sci-fi. Those are probably gamma rays. Let's have a little... Oh, yeah, it can.
And if you get too close.
That's right. So let's see if this works.
We have all the financing options. You can
So
do
this-
12 months at 0% interest, and we even have, if you have a larger ticket and you need smaller payments, we can do special financing for 60 months. So just come and see us at any of our locations. The new store is in Covington, Georgia. Y'all come and see us.
Come see the ladies at National Title Pond and get the cash you need today. Maybe this weather has caused some unexpected repairs, or maybe you've just got more month left over than you have cash. Whatever the reason you need cash today, the ladies at National Title Pond want you to come their way. National Title Pond can get you the money to do whatever it is you need to do with the best deal and lowest payments you will find anywhere. At National Title Pond, you can use your car's title for quick and ready cash. National Title Pond, good people helping good people, with offices all across the WLJA listening area. There's a National Title Pond office near you. Visit the
Nothing.
Title Pond can pawn it. Come see for yourself.
Don't forget to take a break and enjoy everything Museum City has to offer in Cartersville, Georgia. Classic and iconic cars, or experience the Booth Western Art Museum, home to the largest permanent exhibition of Western art in the country. Local
All right, do we have any volunteers of any adults who have some keys with a key unlock or locker? See if you can go ahead and press it, and let's see if we can receive it. Now, I'm not really recording this, so I'm not going to actually. All right, let's see. Try to press it. Oh, you see that? You see that little blip there? Here, let me move over the frequency to where that was. Can you hit that again? Here, do it again while I'm away from the computer. You see that? That's pretty crazy, huh? Now, anyone else? You got one you want to try? That's crazy. So they're both on the same frequency. Was it? Oh yeah, wait, let me move over to yours 1 second. Try it again. Pretty crazy. Ooh, that's kind of strange. Huh. Wait a minute. Is it still going? Well, that's actually interesting. We might have discovered your thing might be doing more after you stop pressing it, which is kind of surprising. And that can happen. Here's mine. So kind of wild. All of these different cars are all on the same frequency, right? So, yeah, yours is still going. That's kind of strange. And yeah, that is weird. You can still see it sending.
Some car keys actually do unlock other cars.
Now, how is it that, oh yeah. And this is a good thing to do with hacking. Sometimes you think something's not doing something, but because you can't see it unless you have a tool like this that lets you see it, right? But a real quick question: how is it if they're all on the same frequency? How is it that they don't all get unlocked by the same key? Any guesses? Yeah.
Is that connected?
kind of. Well, ultimately what it is they're actually transmitting different codes, but they're doing the same frequency. They're doing it on the same frequency, but with different codes. So, but here's the crazy thing. If you have a tool like this, you can potentially record the unlock button and then just replay it and unlock someone's car. So I've actually demonstrated this at hacker conferences before. It's kind of crazy. Yours is still going, isn't it? Well, it could be something different. Oh, it could be something different. So there's all kinds of things transmitting on the frequency. But here's another thing that's kind of crazy to think about. All these different radio stations, they're all transmitting at the same time. How is it that we can hear one but not the other?
What's the one near 313?
Near.
Darker area, it looks like.
Let's see. Yeah, I don't know what that is. But there's all kinds of stuff. There's all kinds of stuff around you. There's that signal again. I don't know. Yeah, I don't know what that is. But it's kind of crazy. All this stuff is always going on around us, right? Pretty wild. 312. Yeah, I don't know. I don't know what that is. Yeah. But, it's crazy because you can tune into everything. You can get Wi-Fi, Bluetooth. You can also, so I did a demonstration years ago. If you ever have like security, like wireless security systems, sometimes you'll have a magnetic sensor on like a door or a window, and it will have to transmit the signal that, hey, I got opened to a hub. So we used to have one of these security systems up in Milwaukee. And I realized you can actually just jam the signal. And then if you open the door, if the sensor can't send its message to the hub, the alarm doesn't go off. It's crazy. How do you jam a signal? Probably shouldn't be getting into all this stuff because borderline illegal stuff. Don't try this at home, kids. But yeah, that's right. But ultimately, it's kind of just like how you jam someone's verbal communication. Let's say me and Rafe are trying to talk, and someone starts yelling. I may not be able to hear what he's saying, and vice versa, right? Works the same way. You can just transmit a loud sound at that frequency, and that jams the signal. It's as simple as that. All right, so that's radio stuff. We will in just a minute. All right, so that's some of the cool stuff. You can do all kinds of crazy stuff with waves. But let's talk about some of the mathematical properties of waves. What makes waves waves? So ocean waves, you can see like this. Real quick, though, I want to have a little graphing tangent. So I want to talk about graphing. I'm guessing most of y'all haven't got into graphing functions before. And so I want to do a small demonstration because this will help us understand some other mathematical stuff. So graphing a function works like this. Y equals x. So basically, this is a way of showing what a math function looks like. Basically, this is called the x-axis, and this is called the y-axis. And basically, the way it works is you just plug you plug the values of x into a function like this, and it gives you the y. So this function, x equals y, says whatever value x is, make y that same value. So for example, at x equals 2, what should the value of y be? 2. And it is. So wherever the line intersects with this y-axis, this is called the y-axis, that's the value of y. So at x equals 2, y also equals 2. What if we do, yeah, right.
Y2.
Y2?
Yeah, you didn't type in any number, so y makes it 2.
Well, it's for every value. So at x equals 4, what should the value of y be?
4.
4. And it is.
Oh.
Now, what if we do the function y equals 2 times x, or 2x? So here, if the value of x is 2, what should the value of y be?
1.
Close. That's, no.
4.
Y equals 2 times x.
3.
No. Any other guesses?
5.
We're getting really close.
4.
4, yes. So what's 2 times, if y equals 2 times x, if the value of x is 2, the value of y should be 2 times 2, which is 4. If the value of x is negative 2, what's negative 2 times 2?
Negative 4.
Yes, and the value there, negative 4. You can also have functions that are what's called nonlinear. So x times x, for example, has a more interesting looking graph. So this is called a parabola. It's y equals x times x, also called y equals x squared. So if the value of, let's say, x is 0, what should the value of y be? What's 0 times 0?
0.
Yeah, and it's 0.
Times anything is 0.
Right. If the value of x is 1, 1 times 1 is what? 1?
Yeah.
And it's 1. That's where the line. So that's just a basic introduction to graphing. We're not going to go too deep into it, but it'll be valuable to understand some of those basics here in just a minute. Actually, I'll show you one other cool function. So this, by the way, this graphing program essentially shows where the two sides of the equation are exactly equal. All right, so when the left side is exactly equal to the right side, it shows the line there. There's another graphing program, y equals x times x. This is actually a program I made called TruThyGraph.
It also has a fuzzy level.
Yes, it's got a fuzzy level. This actually shows not just where the two sides are equal, but also close to equal. So the fuzzy stuff is kind of where it's not exactly equal, but it's close. It's called an error gradient. Anyway, back to the mathematical nature property of waves. Harper. All right. Here's what makes waves waves. How do we think about them mathematically? There's a few different features. Amplitude is the first and one of the easiest. Can anyone explain what amplitude means?
Amplify.
Amplitude. Basically, the amplitude of a wave is how big the wave is. So how if you're singing, that means how loud it is, right? So I'm going to increase my amplitude. Okay, I'm going to start at a low amplitude and increase it. You ready?
Can I try?
Yeah. Yeah, that's very high. That was a higher frequency. The next attribute of waves is frequency. All right? So frequency is how fast the wave is going back and forth. All right? And it's measured in hertz.
Just metric.
Yeah, we will in a minute. So how fast it's vibrating back and forth or up and down. All right? Now a wave, typically, there's one other attribute called period or wavelength. And that's basically, and we're going to have a little food demo in just a minute to help understand phase, all right? Or, sorry, period, wavelength. But basically, one wave is considered when it goes one full cycle. So if that wave repeats multiple times, it can repeat forever. But one period is how long it takes for that wave to go all the way back to where it began. So if we do so like this would be one phase of a sine wave right here. Let me draw this again. So like this would be one phase, goes up, goes down, comes back to the middle. And then it goes up, goes down. That's two phases of the same wave. This is one phase, this is another phase, and it can just keep doing that forever, right? But the phase, sorry, I keep saying phase. The period, that period, that's one cycle of the wave. Now, if the wave does that's one cycle, this is 2, This is 3. If it does 3 cycles, let's say in 1 second, that's called 3 hertz. H-E-R-T-Z, hertz. So that's what hertz means. It's a measure of frequency, of how quickly the wave is vibrating. Yes?
So that means the higher the hertz, the more it hurts?
That is true, actually, in some ways. And we're going to have a physical demonstration of that in a minute. So let's see. We're going to hand out a few gummy worms to...
This is my part for now.
Here,
I gotta demonstrate addiction.
hold on. Let's see here. And here, can you hand these out? And paper towels to...
How many?
Maybe 3 to each child. And so what I want you to do with the gummy worms, we're going to have 2 demonstrations. All right, so maybe don't eat these if you're trying to avoid pork, actually. I thought these were gluten-free, but... Anyway, we're going to do a little demonstration of these to show a wave, how a wave repeats.
Can I do the picture right now?
Hmm? Actually, I think it's going to be hard to show, and we're not going to hand them out to everyone. Hand them out to anyone who wants it, though. Would you?
Who wants some? Raise your hand.
Okay. I think they may have gelatin, actually. I tried to get them without anything, but I guess they have some gelatin in them.
Alright.
You just go ahead and hand them to anyone who wants them.
Who? Raise your hand. Oh, you guys.
Can you pass these out too, Ricky? If they're on the ground, just throw them out. We have plenty. That's fine. You can get more if you need.
Who else wanted some? You?
Okay, and Rafe was going to demonstrate a little wave. Here's- All right, so Rafe is going to do a little demonstration on another form of waves.
Addiction waves. Delicious. It's awful and I need more.
You need more? What do you mean?
It's so good, I need more.
Explain a little more.
Tastes so good in my mouth. Once I swallow, I need more.
Where are you on this wave here?
Up?
When you eat it, you're happy,
Yep.
and then what happens?
I swallow, it's going down.
And you get sad and you want more. And that's how addiction works too. All right. All right. So here's just another image to help you understand the different parts of waves. So amplitude again is how high the waves are, and frequency is how quickly they're oscillating, like this. Oop. Like this. Now, I want to do a little demonstration. So can all of the kids stand in a line? We're going to try to do a wave. All right. Maybe start there. Go along there. That's where most people are at. Everyone maybe form a line right around here. Everyone stand in a line. All the kids stand in a line. We're going to try to make an actual wave. All right. So this way. Line can go over there or over here to the E. you follow what I do, and then you follow what he does, you follow what he does, you follow. So everyone follow the person to the right of them, all right? So we're going to start with going down. Now wait till the person right beside you does it, all right?
Do it.
All right, let's see. Good.
Go.
And so you can just keep an eye on the person right to the right of you. You don't have to look.
People on this side.
Yeah, just look toward me and look at the person next to you. And now we're creating this wave that's traveling, right? Now, okay, there's two things. So the higher the amplitude, the more energy the wave has, all right? So the further you go down, the harder it is. So let's do the small ones like this. That's pretty easy, right? Pretty easy to go down a little bit. If you go all the way down, though, all the way up, that's harder, right? That's harder than going down a little bit and up a little bit, right? But also, so the higher the amplitude, the more energy. Also, the higher the frequency, the more energy, okay? So let's try to go up and down faster. Is that harder or easier than going
Harder.
slower, right? So the higher and lower you go, all right, you can go ahead and sit down. All right, so the higher the amplitude, the more power, but also the higher the frequency, the more power. All right? That makes sense? Now, here's a nice application. Electricity. Anyone know what electricity is measured in? No, say. Ah, good. Watts is the form of power, yes. There's two other things that are often used to measure electricity. Anyone know the other metrics? Volts is one. There's one more. Amps. Volts and amps. So what is the relationship between volts, amps, and watts? Well, amps are a term for amplitude, how big the waves are. Guys, volts are the frequency, so how quick it's moving up and down. Watts equals amps times volts, all right? So the higher the amps, that's going to make the watts go up. The higher the volts, it's going to make the amps go up. Yeah?
Which is more effective? Which is more dangerous? Getting shocked twice time with more amps or more volts?
Usually amps is considered worse. So here's just a little application. Let's say that you're shopping for a space heater, an electric space heater someday. All right? So you got two options. You got this big one here, all right? It's, you've seen this guy before. It stands about this tall off the ground. It's usually about this wide, you know. So that's one option. And the other option is this little bitty one. It's about this size. Well, the question is, which one's going to put out more heat?
The little one could close instead of the big one just heating up.
Good guess. Any other guesses?
Whichever one has more watts.
Well, what would you say? Yeah, good guess. Ray says whichever one has more watts. He's kind of cheated because he helped me with this a little bit, I think.
Actually, I didn't know about this.
Okay. Well, anyway, if we look at the wattage, and again, wattage is a measure of the power, so it's volts times amps. This little one is 1,500 watts. This big one is also 1,500 watts. So even though the big one is like 3 times the size, they actually put out the exact same amount of heat. Kind of surprising.
The other one just sits there.
It's true. Yeah.
If you put a little one, maybe real hot.
It will warm up it.
Does one have a bigger area? Yeah.
Well, no, they actually can do the same area. But you are right, Harper, that it would probably heat you up if you're standing in front of it quicker. That's true. Oh, yeah, they're great. All right.
It's like a light bulb and a flashlight. The flashlight pulses in one direction.
Mm-hmm.
The light bulb pulses in all directions, right?
Something like that. All right, now we're going to talk about just another aspect of waves. So sine waves in particular, I'm going to redraw this. So again, the shape of a sine wave goes like this. Up, down, back to middle. Up, down, back to middle. So there is a very close relationship, y'all. There's a close relationship between circles and sine waves, all right? Now I was going to try to find a good way to show this. This might be hard to see, but we'll see. So I'm going to demonstrate with this wheel. Huh?
Roll to me and I'll roll back.
No, that's not quite. It's going to work. So if you look at just the orange little thing I have taped on here, if this is moving sideways, if you looked at it from the side, the shape it would make is actually a sine wave. All right? So I don't know if you can tell that, but it's like it's actually creating something of a helix, like this, going through space. And a helix is actually related to sine waves. A sine wave is basically seeing just the side of a helix shape. All right. So let me see here. One other interesting thing I want to try to get you to understand is that the sine waves are essentially the shape of energy. They're actually continuously moving and continuously changing. And just so a quick introduction to calculus. So this is, I know this is getting kind of ambitious because we're talking about topics that are usually junior to senior in high school up to college, all right? So it's okay if you don't understand all of this, but now I'm going to graph a sine function. So y equals sine of x. I'm going to make it a little bigger by multiplying it by 2. Okay.
Does sine have an E on the end?
Yeah, it does, but it's usually shortened. So in calculus, there's two main concepts. One is the concept of a derivative. The other is an integral. We're not going to get into integrals, but I want you all to try to understand derivatives, okay? So intro to calculus. Derivative. Fancy word. Derivative just means slope, all right? So let's look at this. So for example, the derivative, basically it's saying is, think of this like a mountain road, okay? Think of this sine wave as a mountain road. And imagine you're driving along this road, all right? Now, when you're going up, when you're driving up a mountain, that's called a positive derivative. The derivative is positive because you're going up. The slope is going up, all right? And then when you're going down a mountain, the derivative, so pretend this ruler represents the derivative. When I'm driving up a mountain, the derivative is positive. When I'm driving down a mountain, the derivative is negative. Now, can anyone, this is kind of a little question challenge. Rafe, don't answer this one. Can anyone say on this graph, where is the derivative 0?
Right in the middle.
Right here? No, right there, the derivative is actually positive because we're going up. All right?
Oh, so it's the bottom or the top?
Yes, the bottom and the top. So at the very top, at the top of the crust, and at the bottom, the troughs. At those points, the derivative is actually 0. All right? So, one cool thing about waves, so let's graph a function like this. The slope always stays the same. So if we graph, so the slope here would be, it would always be 1. If we were to graph, it would always be 1. But with sine waves, the slope itself is always changing. And it's actually changing like a sine wave. That's as far as we're going to go with that. I don't want to try to get any further into that, I don't think. All right. So now we're going to talk about another cool part of waves, which is wave interference patterns. Has anyone heard of wave interference before? Yeah? I actually do art with waves, and I meant to bring a few pieces, and then I just forgot. But I can show you some videos that I made with waves. So this is a wave interference pattern right here. And you may have seen this kind of, does this shape remind them of anything they've seen before?
It looks like a chameleon.
Hold on.
Maybe a speaker?
Speaker? What'd you say? Speaker. Anyone else?
Owl's eyes.
Yeah? Huh? Oh, yeah, big time. Yep. It's also, yeah. Yeah, it could look like that. Rafe, sit down. Ooh, I like that. Magnetic. Rafe, sit down.
I'm trying to block my face.
Magnetic field, yeah, is another very good one. This pattern actually shows up in many places in nature. But if you have a magnet, let's say this is the North Pole and that's the South Pole. If you put like metal filings around it, you'd actually see this kind of pattern. And we're going to talk about how these patterns are formed in just a minute. But you can see how this goes. Now here's one cool thing. Look at this little video, okay? This video is 1 second long, all right? This little one I'm showing right here. It's 1 second. And that is showing one phase. So just like this, right? But remember how I said if you have one phase of a wave, you can repeat that forever, all right? So watch what happens as I repeat this video. See if you notice something, all right? Now here, I'm going to put it on auto repeat and watch what happens. It seems like it just keeps going forever. Now it's kind of laggy, so you actually see a kind of lag there. But if you notice, you could even follow one of these. Let's see where it comes out of the circle here. It seems to keep going all the way down. Forever. And so there's this cool relationship with waves between the finite, like a single phase of the wave, and infinity. Yes?
How many phases does it take to get from one owl eye to the next?
I don't know. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. About 12, I think.
Cool.
So that's kind of a cool little art, just to show a couple other what things can look like with waves. Look at this one here. So this is actually another wave interference pattern, and it's actually it's just like the other one, but more complicated and more stuff going on.
Looks like Gengar.
Yeah, a bunch of strange looking patterns kind of show up in it. And it's kind of crazy because at any point, if you look at any point, it's always changing. Every point is always changing.
How long is this video?
Yeah. It's about 12, this one's about 12 seconds, but you can't tell when it loops though, basically. It goes on forever. All right, so that's kind of wave interference. But let's talk about, so how does wave interference work? All right, now this has some applications in some areas we'll talk about. So, have you all ever been to the ocean or the lake or something, and you notice that some waves are bigger than others? Like maybe you're standing on the shore, and the waves are coming up, but they're not hitting you. But then at some point, a bigger wave comes in, your feet get wet.
And it knocks you over.
Yeah, or maybe it knocks you over. So how could there be some waves that get bigger than others? The answer is wave interference. And so basically, different waves, when they interact with each other, there's two kinds. There's what's called constructive interference and destructive interference.
So it's destructive.
So can anyone notice the difference between the left image and the right image?
Two add together make one bigger on the left, and the two add together make one smaller on the right.
Right. Yeah, and so basically the waves are the same, except these ones are what we call out of phase. So when the top one's going up here, the bottom one is going down, right? Like this. So the waves, if they're going at the same time, the wave added together, they get bigger, right? But if they're going in opposite directions, they actually cancel each other out. This is actually, so if you ever hear of noise cancellation, like noise canceling headphones, this is how it works. The noise canceling headphones are trying to figure out what sound is coming in, and they try to produce waves that are going in the opposite direction. So that's how noise cancellation works. But that concept, that actually, all the kind of cool patterns that you see in something like this, the places where it's brighter here are where the waves are adding together, and the areas where it's darker are where they're canceling each other out. Yeah, Langston.
How does mics work, like for gaming and stuff?
Mics?
Yeah, like they can talk to, and then like say you're somewhere else and you can hear it while you're turning it.
Well, ultimately, microphones usually work with something called a piezoelectric system, where there's a little thing that expands and contracts with the pressure waves in the air, and it converts it to electrical signals. But a little more complicated. Yeah? Hmm? When you're close to a microphone? Well, if you're speaking into a microphone and you're really close to it, it'd be like if you go and talk to someone in their ear really close. It's going to sound louder, right? So that's to say, the amplitude is higher when you're close to the source, basically. All right. And this is just showing the same thing, right? The two waves, when they're in phase, the green and blue added together make this pink one. But here, the green and blue waves, because they're going in opposite directions, if you added them together, it'd be zero the whole way. Now, we're not going to get into quantum mechanics, but I'm just going to mention it briefly, because this is actually touching on one of the most famous scientific experiments in history, called the double slit experiment. So basically, with the double slit experiment, without getting into it too much, scientists have shot things like electrons through two slits, and if you're watching them, they seem to create two lines, just like firing little cannonballs or little bullets through two holes. But anyway, if you're not watching, it creates what's called a wave interference pattern. And that's because the photons, or the electrons you're shooting, actually act like waves, and they actually interfere with each other, adding together or subtracting from each other in different places. And it can create this wave interference pattern. And that's getting into some college level stuff, so we're not going to talk about that too much. All right, but so also on waves, interference patterns, convolution just means adding together. Superposition basically means that waves can be added together. And so this right here is actually a little picture. So if you ever look at sound waves, like a recording of sound waves, they often look like this. And this is actually a picture of a sound wave of me saying, ah, like that. So what is the frequency of this wave here? Or I mean, I guess you can't tell the frequency, but where's the peak, right? Well, the peak is here, and here, and here. But there's also these smaller seeming waves added in there. All right? And these are actually called harmonics. So this is actually, this is another way to look at it. This is a recording of, I think, me singing do, re, mi, fa, sol, la, ti, do. And this is showing the frequency. But here's the crazy thing. It's not just one frequency. There's actually all these other frequencies that show up. So if I'm singing at a 100 hertz, there's also about a 200 hertz sound, and a 300 hertz sound, and a 400 hertz sound. And these are called harmonics. But all these things are added together into the sound waves and the pressure of the air. And so one cool thing about waves is you can add them together, but you can then break them back apart. And this is how radios work. Okay, so think about this. There's all these different radio stations broadcasting, right? Some of them are broadcasting at 97 FM, 97 megahertz. Some are at 100 megahertz. But how can we tune into just one? Wouldn't they all interfere with each other? You would think maybe so. But ultimately, waves added together, they kind of look like this when they're added together. So this is adding two sine waves together. All right? So this is a 1 hertz sine wave added with a 10 hertz sine wave. But interestingly, you can always break them back apart. That's the concept of wave superposition. And this is a picture, actually, so you can see where, there's these bigger waves, these big mountains, and there's all these littler waves inside. But waves are basically, you can break them back apart. Yeah, we're not going to get into that too much. And we talked about this already a little bit, just the relationship between sine waves and helixes, right? Again, a sine wave is basically just seeing a helix from one side. And it's interesting to also think about even our solar system is actually basically a bunch of waves, a bunch of helixes shooting through space, right? You got the sun. The sun's not in one place. It's actually moving, and the other planets are revolving around it like a helix. And lastly, the wave nature of reality extends beyond just physics, and I think it actually goes into metaphysics, you might say. So there's a Bible verse, whoever exalts himself will be humbled, whoever humbles himself will be exalted. And this is how waves go, right? If the wave is high, guess what it's about to do?
Go down.
Yeah. And if it's down low, guess what it's about to do?
Go up.
Go up, right? This girl here, is she about to go up or down, do you think?
Up.
Down. How about that girl there?
Up.
Yeah. This vibratory nature of reality, it's everywhere. It goes throughout all reality. And these waves, they pop up everywhere. They pop up in sound, they pop up in radio, they pop up in your heartbeat, just about anywhere you can imagine. So that's it, guys. Thanks for listening and attending.